Thank you and welcome to this channel, that is Teacher Stephen Omondi, okay's channel. Today we are going to at least unpack and mystify these quantum numbers and electron configuration. This is a lesson that can be enjoyed by university students who are taking chemistry 101. That is year 101. Basically, if you take the unit, you will really enjoy this video. Otherwise, remember to subscribe by clicking the subscription button for more video, because every week we post at least 2 videos explaining the concepts in chemistry. Otherwise, work with me as you enjoy part of this lesson. So first of all, let us first of all know the 4 quantum numbers. The first quantum number is the principal quantum number, which is denoted by letter N. And this tries to just explain the energy levels or the shells within the shells of electrons within an atom, as explained here. So it describes the energy levels of an electron an electron inside an atom, and also gives the size of an atom. So the N can be any positive number, that is from 1, 2, 3, 4, and even more. So if you check this, we have said that it contains 1, 2, 3, 4. So as the number of N increases, to mean as the number of N increases, the atomic size also increases. So that is why we have said that it describes the energy level of an electron inside an atom. Also, it also gives the size of an atom. For example, let me check you here. For example, if we have this, if we have this, that is the nuclear, then we have this. So the first one here, N, maybe N is equals to 1, and also here N is equals to 2. So as the number of N increases, we call them the energy levels, also gets away from the nuclear. So the N, so like, for example, if N shows just the energy level, so like 2 to mean it is energy level number 2. And if N is equals to 1, that is energy level number 1. N is equals to 3, that is energy level 3. Like that. So what I want you to, maybe what you should be able to understand, what is this principle that is the quantum number dealing with. So it describes the energy levels, or the energy levels or the shells of the electron, and those electrons are inside an atom. And also it gives the size, because we have said as the number of N increases, the size of atom also increases. So it also describes or gives the size of an atom. Let's see another one. Another one is called the angular momentum, or we call it azimuthal quantum number. It is denoted by letter L. So this one, it gives the information on the shapes of the orbitals, which electron is located. So orbitals are just the path, the circular path surrounding the nucleus of an atom, and those paths are fixed. So when they are fixed, to mean what moves, you know, the electrons, the movement of the electrons in an atom, also the same as just how the earth rotates. You know, the earth is fixed, but now what revolves, not the how the earth rotates. So what makes it revolves is just the same scenario which is used to explain the orbitals. So the orbitals are where the electrons, the space where there is a high probability of finding the electrons. Those are the orbitals. And also, so we have said that the azimuthal gives the information on the shapes of the orbits in which the electrons is located. For example, when L is 0, it gives us a shape which is S shape. The S shape is for the spherical, to mean the electron or the orbital. The orbital is in spherical shape. And when S is 0, to mean we have something that looks like this. So this is what, this is the shape of the first shape when the L is 0. So in this case, L is now 0. And when L is 0, it means that N is 1. Because how do we get L? It is N minus 1 will be able to get the shape. So in this case, we have only one orbital. When S is when the shape of the orbit is in spherical, to mean that is S, always L is 0. And that means we have only one orbital. Then another one is this one. Another one is when L is now 2, when S is also 2. I mean, when L is 2, when L is 2, no, when L is 1, I mean. The other time, so P is when the shape is at P, which is the P means the dumbbell shape or the lobe. It is dumbbell shape. So when the orbital, all the orbitals are in a dumbbell shape, to mean L is always 1. And when L is 1, to mean we can have 3 orbitals, which we'll again explain later, because M is what gives us the number of orbitals. So, and N, when L is 1, to mean M can be -1, 0, up to +1. So if you count this one, there are 3 orbitals. That is why at P we have 3 orbitals. We have Px, we have Py, and we have Pz. So when L is 1, which is always P. So for example, if you've been told 3P, 3P like this one. So how can you now be able to maybe to get n and what have you. N is always the coefficient of the the shape. So maybe the coefficient of P here, n, will be now 3. Then this P is always the value of L, which is 1. P is 1, S is 0, like that. So that is how you should be able to, get that. So very good. So we have said at P we have 3 orbitals. 3 orbitals. 3 orbitals. And each orbital can carry a maximum. Each orbital can carry a maximum of 2 electrons. Like p orbitals carry up to 6 electrons, because s orbital carry 2, then 6, then from there we have 10, then lastly 14, which we'll be able to discuss as we go. So another one is now d orbitals. So the d shape, we are still explaining the shapes of the orbitals. So like this one, L is equals to, at D, L is equals to 2. Is equals to 2. And D means the double shell shape, I mean, the double. So if you check them, they are double. This is 1, in 1, then this is 2. So it is a double shell, double shell. You should be able to know that. So in this case, we have 7 orbitals, because when L is equals to 2, when L is equals to 2, it means that for us to get M where we have -2, we'll have -1, we'll have 0, we'll have 1, we'll have 2. So there should be 5. That is 1, 2, 3, 4, 5 in that case. So in D, in D, we have 5 orbitals. You can check them here. We have dxy, we have dxz, we have dyz, we have dx squared minus y squared, then we have dz squared. So in dz squared, there is that ring. You should be able to understand this very well. So in that case, this is a double dumbbell shape. We have double dumbbell shape. So that is what you should also be able to know. So in this case, the D can carry up to 10, because I said each orbit can carry a maximum of 2. So 2 times 5, you will get 10. So you realize that this one will be 10. So how can we get that? It is always 2 into, you multiply 2 times the P. So here we have not P but D. In this case, D, we have 5D, so 5 times 2, you'll be able to get 10 in that scenario. Then the last one is the F. The F1, the F means the shape is very complicated. The shape is complicated. So in this case, there should be 7 orbitals, where we will have 1, 2, 3, 4, 5, 6, 7, and each carries 2 electrons. So 2 times that to mean F carries a maximum of 14 electrons. So you can see that like that. So another one is magnetic quantum number. So the magnetic quantum numbers only describes the number of orbitals within a subshell. The number of orbitals within a subshell. For example, M we get from L. If L is equals to 3, if L is equals to 3, we can get the possible values of M from this one by saying that M is always from negative L to from negative L to positive. It goes up to positive L. So like here we have negative, we have 3. So that is M will be negative 3, negative 2, negative 1, then we have 0, then we have positive 1, we have positive 2, we have positive 3. So those are the M, that is the magnetic quantum numbers. They describe the number of orbitals within a subshell. So if this one, if the subshell N, L3, so the 3 can carry an orbital, 7 orbitals. That is 1, 2, 3, 4, 5, 6, 7. So those are 7 orientations, or the 7 orbitals within that subshell. That is also what you should be able to know. Then let's check another one. When you are maybe told to get when L is equals to 4. This one also you should be able to get. You begin from negative 1, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, up to 4. Then you will be able to get the number of orbitals within the subshell. In other words, how can we get the number of orbitals? The number of orbitals can also be gotten when you have N, that is N, you multiply N by 2. You will be able to get the number of orbitals, which are the number of energy levels. For example, let's take, for instance, if N is equals to 4, then you are told to get the orbitals. In this case, when N is 2, when N is 4, L, that is L can be either 3, that is 0, 1, 2, 3, because L should be from 0 up to, it can be 0 up to N minus 1. So if we begin from 0 and N was this one, then it reads from 0, 1, 2, 3. This 3 is gotten from 4 minus 1, like that. So from here, we can also get M. So M, when L is 0 is 1, to mean there we'll have only, that is the s orbital, where we have only one orbital. That is S shape. So that is what you should be able to know. We have only one orbital in that case. When L is 1, we'll be able to get negative. When L is 1, M will be -1, 0, 1. So there we have how many orbitals? We have 3 orbitals. Then from there, if it is 2, we'll have -2, we'll have -1, we'll have 0, we will have 1, we will have 2, like that. So that is the last one. So if you count this, it should be 5. So that is 1, 2, 3, 4, 5. So there we have 5 orbitals. Then if we have a 3, where we'll have a -3, -1, not -1, but -2, then -1, then 0, then 1, then 2, then 3. So if you count this one, they will be 7. So if you add all these orbitals, that is, here we had 1 plus this plus 3 is 4, 4 plus 5 is 9, 9 plus 7 is 16. So these are the number of orbitals which are in an atom with n is equals to 4, with 4 principal quantum number. In other words, for you to get, just the way I said, for you to get the n, for you to get the number of orbitals, sorry, it is n raised power 2, not n times 2, sorry, should be n raised power 2, should be n raised power 2, make that correction, sorry, it should be n raised power 2, so that is 4 raised power 2, which is 4 times 4, you get 16, sorry, make that correction. Otherwise, thank you, and let's proceed on. Another one is a spin or spin quantum number denoted by letter S. So spin quantum number, it just gives the direction, the insight, it incites, or it gives the exact direction in which the electron is moving to or spinning to. So there are only 2 possible values of S, that is +1/2 or -1/2. So that is what you should know. So always the electrons, they have unique quantum numbers. They cannot have the same quantum numbers. Electron cannot have the 4 identical quantum numbers at the same time. So for example, if we have this one, always if we have this one, if here is +1/2, then this side will be -1/2. That is, when you are representing this in orbital diagrams, one will have an arrow facing upward, another one will have an arrow facing downward. So these are the electrons. The same electron cannot have the same spin quantum number. So if one has this one with an arrow going upward, which is +1/2, then the other one will have to face down with a spin of -1/2. So that is what you should be able to know. Then we have another one here. After discussing those 4 quantum numbers, before we go to electron configuration, it is better we learn about these rules and maybe the principles and the rules. The first principle is the police exclusion principle. Police exclusion principle, it tries to explain that no two electrons in the same atom can have the identical values for all the quantum numbers. So no two electrons in the same atom. Maybe we have, this is our first atom, the first electron and another electron. These electrons can never have the same values of the 4 quantum numbers. They can share n, they can share m, they can share s, not s, but m, but they will never share s. So one of the quantum numbers must be different. They cannot, the electron of the same atom will never share the same or the identical 4 quantum numbers. You should be able to know that when n is equals to L and also is equals to M, then S will never be the same or will never be equal. Another principle is Aufbau principle. Aufbau principle states that the electrons will fill the lower energy atomic orbitals before filling the higher energy ones. That is, you cannot fill 2s before filling 1s. So you have to fill the 1s is when you go to 2s, and also you cannot fill maybe 3p before filling 4s. Just like that. So it follows the chronological order. So you have to fill the energy with the lower orbitals before filling the energy with the higher orbitals. And the energy, the number of orbitals are gotten with n plus L. You will be able to get the number of orbitals. For an instant where we have when we have maybe 3s and 4p, 3s and 4p. So which one will you fill first between 3s and 4p? Let's see this one. So let's get the number of orbital here. So it will be 3 plus this s, we add that L. L is 0 at s. That is what you have to know. So when you add this, you will be able to get 3. Then this one 4 plus p. P at p, L is equals to 2. Not to 2, but to 1. Like that. So we'll have 5. So which one will you fill first? You will have to fill this 3s before filling the 4p, because this one is lower than that one. So that is what you should know. That is n plus L. And here L, we have gotten L is at S is 0. N at P, L at P is 1. L at D is 2. L at F is 3. So that is what you have to know that. So after the half-bow principle says that you feel the lower energy level of atomic orbitals before feeling the higher energy levels of the same orbital, the orbitals of the same atom. Another one, the last one here is Hund's rule. So Hund's rule says that every orbital in a subshell is singly filled or occupied with one electron before any one orbital is doubly occupied, and all electrons in singly occupied orbitals must have the same spin. What do this person mean? It means that maybe if we have 3p, so P we said in P we have 3 orbitals like that. So when you are feeling this, maybe it was 3p6. So when you are feeling this one, you first singly fill these orbitals before doubly filling them. Then you come back to this side is when you fill them like that, to mean you cannot fill them in this manner. You can't fill them in this manner. Maybe here. So that one will be wrong. And again, when they are singly filled, they should have the same spin. Like the first one, you see the spin was positive a half, like that, all of them like that. And we continue. Let's see this one. We have this one. Write the electron configuration of the following elements using SPDF notation and draw its orbital diagram. So for you to understand this, you must be able to understand the above principle that we have just learned. That is, we have 1s, 2s, 2p, 3p, not 3s, I mean 3s, 3p, 3d. Then we have 4s, 4p, we have 4d, and 4f. So long as I know you know this rule, that this one goes like that, that one, this one, this one, this one, pivot. So you should be able to know that. So let's see how this one work. So this one has got 14. That the first one is magnesium with 12 electrons. So the first one will be 2s, and s can be occupied by a maximum of 2 electrons. Then we'll have 2s occupied also by 2 electrons. So if you add so if you add this one, the electrons, that is 2 plus 2, we'll have 4. So still remaining 8. So if you see that 2p, p carries a maximum of 6 because p at p, L is equals to 1. And 1, if you count from -1 up to +1, you'll get 3 what? 3 orbitals. And those 3 orbitals, in each orbit, it carries 2 electrons. So 2 times 3, you'll get 6. So P can carry a maximum of 6 electrons. Then lastly, we will have that 3s. So if you add this one, 3 plus 2 plus 2 is 4, 4 plus 6, 10, 10 plus 2 is now 12. Then let's see that one. So this one will be now the first S. We are now drawing the orbital diagram. So this is the first one, which is 1s. And S, we said, can carry a maximum of 2 electrons. And those 2 electrons should have the opposite what? Spin, because they should have opposite spin. They cannot, in the same shell, they cannot have the same spin. I mean, let's see, that is 1s. Then you can see that is the first one. Then the second one, which is of opposite. Then from there, we go to 2s. So 2s, that is the box for the 2s. You can see that as 2s there. Then also in that box, it carries a maximum of 2 electrons with the opposite what? Spin. You can see, just like that. That is how you will fill them. Then we go to now 2p, and p has got 3 orbitals, or the sharp cells. 3 sharp cells. You can see those are 3 subshells of 2p. It should be 2p, not 3p. You can make that correction. It is 2p, because you can check here it is 1, then you come to 2s, then 2p, 3s, like that. So in here we have used the laws that we stated at first. So the first one, we have said that we should fill the lower energy levels of orbitals before filling the higher ones. Again, if we come to above principle, you now do what? You singly fill the shells or the orbitals using the single electrons, and they should have the same what? The same spin. For example, you can see that one, then we fill this one, then we fill that one. Singly first is when we doubly fill them. That is, now you can see with opposite spin, like that. Then we go to the last one, which is now 3s. So 3s, like that. Then we have those 2 electrons. So if you count all these electrons, they should add up to 8. So somebody can ask you to give the s, that is the spin of the 6th electron. That is, you come and count 1, 2, 3, 4, 5, 6. So that is positive what? Positive a half. Because the 6th one, it points up. And maybe somebody also can ask you to which you get m of the 6th electron. So this 6th electron, where does, in which orbital does it fall? So here we will have, this is P, and P, we said P has got 1 L. So here will be -1, 0, 1. So to be in M, the sixth electron will be at 0 M. M will be 0. You should be able to know that. Let's get to that one. Also, we'll have and the nitrogen will have that one S2, 2S2, 2P3, and if you add all those ones, they are now 7. Then you come and draw the orbital diagrams, where the first one will be occupied with 2 electrons, like that, with opposite spin. Then we'll have the 2s2 with the same, like that. Then we'll have 2p3, where each, because there are only 3 electrons, so each will be occupied by 1 electron in that manner. Then the next one here is chromium. Chromium will have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. So if you add these ones, that is this one, 2 plus 2 plus 4, 10, 2 plus this one, 8, those are 18, 19, 24. So at first, here was 2, then here was 4. So we go for the rule that says that d orbital should be either halfly filled or should be completely filled. So that is why we borrowed 1 from this one, because here there were 2 here at first. We borrowed 1 from this. Here there were 4, so that 1 plus 4 makes it 5. Then there is what is when you are drawing or writing the electron configuration of the transition elements or the transition metals, always they swap. S and D, the last 2, this and this always swap in this way. The way you can see, that one goes there and the other one goes there, so they swap in that manner. So this is the correct electron configuration. But even if you write with 3 here, then 4s here, then there is no problem with that. Then you come and draw like that. You draw 1s, you use the principles of filling that, which is which you should be able to know. So like that, then in this case, you first singly fill it. Like that is when you doubly fill it with now opposite spin. Then now we go to 3s. So there we have that and that. Then we go to 3p6. You singly fill them like this, like that, like that. Then doubly fill them like that, like that. Then we go to 3d5. No, 4s, I mean. 4s, which is now like that. Then, because s was 1, borrowed 1 from there, it gives out for D to become stable. So then we have 3D with 5, like that. So if it could have not given out this this part could have been blank if it could have not gained 1 from S. This part could be blank, and that part should never be blank. So that is now let's see for copper. Copper, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. So before, here was 2 and here was 9. So we said it should either be completely filled or halfly filled. So because it was in need of only 1 electron to become stable, so that one was borrowed from this part. Then we said under the what is called the transition elements, so the metals, S should swap with the D. So like you can see how they are swapping like that. Then it's just simple like that. Then you come and draw the the orbital diagram, that is S1 with those 2 electrons like that, like that, like that, like that. Just as simple you can do within a second, then you are done. Then that one has got then we go to 3p6, that is 1 even like that, then that one carries 10. Just simple as that. Let's see the next one. Write an orbital diagram for the ground state of the ion atom. So ion, you have to know the atomic number of ion, which are 26. There are 26. Then you will have 1s2, 2s2, 3p6, 3s2, 3p2, 4s2, 3d2. So if you add this one, this plus this plus this is 10. This plus this plus this 10. Those are 20 plus 6, 26. So that is the ion. So the ground state electron configuration, because before you draw the orbital diagram, you have to write the electron configuration. Then from there, because we said those are transition elements, they will swap. That one swap with that, like that. Then now you come and draw the orbital diagram. So we'll have the first one is 2s2, 1s2. So we'll have 1, 2. Then we go to 2s2, that is now 3, 4. Then we go to 2p6, we'll have 5, 6, 7, 8, 9, 10. Then we go to 3d6. No, 3s2, I mean. So those were Those were 10. So here also we'll have 11, 12. Then we come here, 13, 14, 15, 16, 17, 18. Then we come there, 19, 20, 21, 22, 23, 24, 24, 20, 25, 26, like that, and you are done. Just as simple as that. You get it in that manner. Then we have another question is identify the element with the electron configuration of 1s2, 2s2, 2p4. Write its orbital diagram and give the quantum numbers of its sixth electron. Very good. So you count this one. For you to identify, you must know the number of atomic number. That is 2 plus 2 plus 4. Those are 6. No, 8, I mean. So which element in the periodic table is atomic number 8? That is oxygen. Let's see. That is oxygen. From there, we can draw the orbital diagram first. So we'll have that one, 1s1, 1s2, I mean, 1, 2. Then we go to 2s2, 3, 4. Then 2p4, we'll have 5, 6. So that is the sixth electron. 6, 7, 8, 9, 8. Sorry, we were to reach 8. So let's come back. So they were up to 8. So where is the sixth electron? The sixth electron is that. So in this one, it falls under P, and P, that is L. You know what gives us the specific position of the orbital is L. So L at P is equals to 1. So we'll have -1, 0, then 1. So to mean, give the quantum numbers. To mean, we have to give P. At P, you can get here, we have to get N, we have to get S, we have to get M, and we have also to get N. So for you to get N is always this whole number, because it is at 2p. That is, the sixth electron is in the p orbital, or the p orbital, I mean. So when 2p, to mean N is now 2. When N is 2, and we have said that P is always 1, and we have seen here is -1, 0, 1, to mean M is now 0. That is magnetic quantum. M is 0. Then the S, this points up to mean it is +1/2. Then you can see this one. We will have N is equals to 2. We'll have L is equals to 1. 1, 2, 3, 4, 5, 6. So here is, sorry, here it should be 0, not 1. So we can make that correction. So here is 0, because the sixth one is here. Then from there we have M, or M, L is 1. That is okay. Sorry. Sorry, the teacher is becoming tired. We have said this, the sixth electron is at 2p. The sixth electron is at 2p. So for us to get N is just, N is this 2 here. Then P, we always know that P is always 1. P is always 1 at, what should I say? for you to understand this well. Okay, we had explained it even earlier. We said that the S, P, D, and F, those are the shapes of orbital, which is explained by the azimuthal quantum number. So azimuthal at P is always equals to 1. At S is 0. At D is 2. At F is 3. So here, in this case, because the 6th electron is at 2p and p is 1, like that. So, and also M, if you follow this one, that is -1, 0, 1, it falls under 0. That is the 0 where M is equals to 0. Then from there, S is now positive a half because it is pointing up. Just like that. Nothing much. Give full and condensed electron configuration and partial electron diagram showing the valence electrons and the number of inner electrons for the following elements. The first one is nickel. The first one is nickel. So we'll have nickel is 28. We'll have 1s2, 2s2, 2p6, 3s2, and 3p6, 4s2, and 3d8. So this one they will swap because they are transition. The nickel is a transition element. Then condensed one, when you are told to write the condensed electron, you should be able to identify any noble gas. Like helium is 2. We have helium, we have argon, we have neon, we have all those ones. So for you to identify, you can, because you know that neon is 8. Then that is helium, which is 2, I mean. Neon, which is 8. We have the name. This one, which is the argon, I mean. The argon, which is 18. So let's see this one. So this, if you count this one, that is 2 plus 2 is 4, that is 10. Up to here is 10. Now that is neon. Then we have this plus that is 18. 18 is argon. So therefore, then this one plus this is 10, but 10 plus 18 cannot fit under noble gas. So we reach at 18, which is now argon. So we write argon in a bracket, then we write the one which are remaining here. So like that. So we'll have that argon. Argon, this one carries this 20 in 18. 18. Then we come and write the one which is remaining there. Like that. This. So we have 1, that is 4, 10, plus this one 18. Then 4s is remaining like that. And it is done. So that is, so you have to master that. So Sorry. Let's continue. Then we draw the partial diagram, orbital diagram. So we'll only draw for 3D8 for S2, which is 3D8 with 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. And what you have to know, there are some 18 electrons remaining the other side. We are remaining with 1s2, 2s2, 2p6, 3s2, and 3p6, which is represented by this argon. Is that right? Let's proceed. Then we go to 4s2, which is that 1, 2, like that. Then you are done. Then you go to the next one. The next one is that SR and SR. The SR is strontium. 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 You can pause the video, then maybe you can write this one. You can write the condensed one, so you can count. This one, we know it is more than 2. If we come up to here, is 10. And also up to here, 20. But what we have to know, helium is 2, neon is 10, argon is 18, krypton is 36, then xenon is 54, radon is 86, and we have oxygen, which is 118. So if we check this one, if we have 1, this is 2, 4, 10. 10, that is 4, 10, 18, 28. 28 plus this is 30. Then plus this is 36. And 36, we said it is krypton, which is Kr. So krypton, which is Kr. So we love Kr and this one. Let's see. That is Kr, krypton, which has 36. And it is a noble gas. When you are writing condensed, you go to the noble, the stable one already. So to me, this krypton stand for 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4ps in that scenario. Then from there, you now write 5s, just simple as that. Then you can now draw that for L5s2, which is drawn just like that. Then you are done. Then we go to the next one, which is polonium. The polonium, that is called polonium. 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 So polonium, there are 84. That is that. Then the condensed one, you can as well count. This is, so it can either be 4, not 4, but 2, 8, not 8, but 10. That is 2, 10, 18, 36, 54, 98, 118. So if you know like that, then let's go. That is 410 up to here 18, 38, 38, 38. That is 4, 10, 18. No, 4, 10, 18, 18, 28, 28, 30, 36, 36, 46, 46 plus this, 60, 60 plus this, 68, 68, that is 98. So we can reach up to maybe 86, because we have 2, 10, 18, 36, 54, 84. So let's reach maybe 54. This plus that up there, that is 10, 18. 18 plus 18 plus 10, 28, 30, 30. This is 40, 46. 46, if you add this, will be 60. 46. Should 46. 46 plus, that is 48. 48. 48 plus this is no 68, sorry. This is 60. 60 plus that is 68. 68, that is 70. 70. This thing reaching 84. Let's add this thing calculator. We have 2 plus 6 plus 2 plus 6 plus 10 plus 2 plus 6 plus 10 plus 14 plus 2 plus 6 plus 10 plus 6. Oh, they are reaching, that is 84. And they are very much okay. So it can be, so that is 10, 18, 38, 18, 28, 30, 30, 46, 46, 46, 46, 60. So we can reach at that is 54. 54, then we'll remain with this one, which is that is from here. So from here are 54. Let's see, 10, 18, 38, 40, 56. So that will be in that order. So if you want to draw that, that is 4F. 4F lava like that. We'll have them being occupied in that manner. And we go to 3D5, which is also occupied in that manner. Then we have that is 6S, which is occupied in that manner. So that is how it will be drawn. So you should, you ought Xenon will be check so that is how we should be drawing it. If I check the atomic number of xenon, (54). So here already we have how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 14, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6. So 26, that is 84. 84 minus 26, we get 58. And xenon is 54. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6. That is just okay. So 84, remember 48. There is what is not adding up here. In this case, 54. Okay, it's okay. That is let's now go to the next one. Sorry for the delay. Also, it was still continuing. We have now we have that where there were 4. 1, 2, 3, 4. Then we have determine the following for an element with atomic number 29. The expanded electron configuration will be just that. So 29 is always copper, so that is that. We had drawn it earlier. The most likely oxidation, that is +2. This is because the d orbital will be halfly filled into positive oxidation. The result in high negative results state that results in high negative enthalpy of hydroxylation that makes it more stable in forming aqueous solution. So the one which is stable is copper 2. We have also copper 1 and what have you. So you should know that. The group in the periodic table to which the element belongs to. So how do we get the group? The group, so what you do, return this one the way it was before. So we'll have 4s, 4s1, d10. So for you to know the group, for this one, you check the outer one, you will get it is in the D block. So in D block, for you to get the group, it is always you add the powers, that is for S and this one, which will be 11. So it will be in group 11, which is written like that. It is 11B. You can either write group 11 be like that. So but for you to get the period is you get, it is gotten from the principal quantum number, where you check the maximum quantum number. For example, if you could, if you check here, we have 1, 2, 3, no, 2, 3, 3, 3, 4. So to mean it could be in period 4. Then we see, sketch diagrammatically the shapes of the following atomic orbitals. For S, it is only 1. For 3p, they are always 3. So you have to draw them 3. I've just drawn 1. The next one, we'll draw that and that. Ensure that you draw them, all of them. Although the outer energy level configuration of helium is 1s2, this element is placed in group 8, the same as group 10, rather than in group 2a. Explain this seeming consistently. Helium is in the group, that is group 18, I mean, group 18a, noble gas, because its outer shell is full. The outer shell of helium is S-type shell that can only hold two electrons, and that is why it cannot be placed in group 12. Write the full electron configuration and condensed electron for ion. So from this ion, it will lose 3 electrons. So that is why we'll have now 23. If you count this one, I think they are 23. So up to here is 10. 10, 18, 23. So that is that. Then you will argon 10, that is up to here is 10. Argon is 18, sorry. Argon is 18. So that is, the teacher is that is 4 plus this 10, 18. So it will be that way condensed. Then you draw. It is in the group 8. And you can now draw those ones. A neutral atom has an electron configuration of this one. So it is this. So when you swap them, let's see. So the one which are remaining before this, we have 1s2, 2s2, 2p6, 3s2, 3p6. So this one, if you add all of them, if you add before they swap like that, if you add all of them, that is 2 plus 6 plus 2 plus 6 plus 2 plus 8 is equals to 28. How many orbitals are partially filled? For the partially filled, these are completely filled, 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 completely filled. So this and that. That is halfly filled, that is halfly filled. So there are two orbitals which are halfly filled. State the group and the period to which the element belongs to. The period is period, let's see, rewrite this thing, where just the way they are, we have this D. So the period, because this is in the D block, you add the power of 8 plus 2, which is 10. So that is in group 10. And period, you check the maximum number of principal quantum. Here we have 1, we have 2, we have 2, we have 3, we have 3, we have 4, we have 3. So to the maximum is 4. So it is period 4, group 10, just like that. Consider n is equals to 4, determine the possible values of L. Possible values of L is from 0 to n minus 1, which is now 1, 0, 1, 2, and 3. I indicate the designation of the subshell. We have 4S, 4D, 4P, 4F, which you can designate in that manner. You can designate them in that manner. Just as simple as that. That is that. Find the possible values of M. So these are all possible values of M. When L is 0, M is that, and that. And the total that we have gotten. How many atomic? We said that is n squared, which will give you 16, or you can draw. Then you get that. Thank you for watching this. May you subscribe, and maybe you can inbox me. I have so many questions that can help you understand this topic or this unit. Thank you, and may God bless you. Subscribe, share. Any comment, I'll be able to respond to that. Otherwise, thank you. Be blessed.